Dark Energy, The Puzzle of Acceleration. Title: Dark Energy, The Puzzle of Acceleration. Introduction, 100 words. Dark energy, an enigmatic force that permeates the vast expanse of the cosmos, remains one of the most intriguing and least understood phenomena in modern physics. As our understanding of the universe expands, so does the curiosity surrounding its composition and behavior. One of the most remarkable discoveries of the late 20th century was the realization that the expansion of the universe is no slowing down due to gravity but rather accelerating. This puzzling revelation led scientists on a quest to unravel the mysteries of dark energy, offering a remarkable glimpse into the fundamental nature of our universe. The discovery of cosmic acceleration, 200 words. The concept of an expanding universe was first hinted at by the observations of Edwin Hubble in the 1920s. Hubble's observations of distant galaxies revealed a constant relationship between their rotation velocities and their distances from us. This relationship, now known as Hubble's law, suggested that our universe is not static but instead expanding. However, the real surprise came in the late 1990s when two independent teams of researchers studying distant supernovae made a stunning discovery. Instead of observing a deceleration of cosmic expanse as expected, they found evidence pointing toward an acceleration. Their findings forced scientists to re-evaluate their understanding of the universe's composition, leading to the emergence of dark energy as a possible explanation for this bizarre phenomenon. Understanding dark energy, 300 words. Dark energy is a hypothetical form of energy that permeates the fabric of space itself, pushing against gravity and causing the expansion of the universe to accelerate. It is postulated to make up about 68% of the total mass energy content of the universe, leaving ordinary matter and dark matter far behind in terms of abundance. Yet, despite its dominance, dark energy remains elusive in the subject of intense speculation. One of the leading theories explaining dark energy involves the concept of a cosmological constant, often associated with the work of Albert Einstein. The cosmological constant represents a constant energy density that fills space uniformly and exerts a negative pressure, resulting in a repulsive gravitational effect on a cosmic scale. This notion provides a possible explanation for the cosmic acceleration observed in our universe. The Puzzle of Acceleration, 400 words. The true nature of dark energy and the mechanism behind its acceleration remains one of the most significant puzzles in modern cosmology. One of the primary challenges lies in trying to reconcile the observed cosmic acceleration with the predictions of traditional physics theories. One proposed explanation posits that dark energy is dynamic, evolving over time rather than being a constant, as the cosmological constant suggests. This theory, known as quintessence, suggests that dark energy is a scalar field with its own properties and behavior. Depending on the specific characteristics of this field, it could induce the observed cosmic acceleration. However, the exact nature of this scalar field remains unknown, leaving much of the theory open to speculation. Another intriguing proposal suggests that the observed acceleration may be an illusion resulting from an incomplete understanding of gravity. Modified gravity theories, such as the well-known modifié de Newtonian dynamics, MOND, aim to explain the acceleration without the need for dark energy. These theories propose that the laws of gravity, as described by Einstein's general relativity, are only valid at certain distance scales, and deviations become apparent at cosmic scales. Although these theories have gained some attention, they have yet to gain widespread scientific acceptance. Future developments and collaborative efforts, 400 words. The puzzle of dark energy requires a multidisciplinary approach, combining observational astronomy, theoretical physics, and computational modeling. One significant future development lies in mapping the large-scale distribution of galaxies in the universe. By studying the clustering and distribution of galaxies, scientists hope to gather valuable insights into the behavior and properties of dark energy. Another area of focus is the study of the cosmic microwave background radiation, CMB. The CMB is the faint radiation left over from the early stages of the universe, and its precise measurements can offer valuable information about the composition and dynamics of the universe. Collaborative efforts among international space agencies and research institutions will be crucial in advancing our understanding of dark energy. The future European Space Agency's Euclid mission, SC, scheduled for launch in the mid-2020s, will map the geometry and evolution of the universe, focusing on dark energy and dark matter. In addition to these future missions, advancements in technology and computational modeling will play a vital role in unraveling the mysteries of dark energy. High-performance computing and sophisticated simulations will allow scientists to explore different theoretical models and test their predictions against observational data. These efforts will help refine our understanding of dark energy, potentially leading to breakthroughs in fundamental physics. Future developments and collaborative efforts continued. Efforts to understand dark energy extend beyond observational astronomy and theoretical physics. Collaborations with experts in related fields, such as particle physics and quantum mechanics, hold potential for groundbreaking insights. One avenue of exploration involves studying the fundamental properties of particles and forces that make up our universe. By investigating the behavior of particles at high energies, scientists can gain a deeper understanding of the fundamental forces at play in the universe. Quantum gravity, a theoretical framework that seeks to reconcile the principles of quantum mechanics with gravity, also offers potential avenues for understanding dark energy. Quantum gravity theory, such as string theory and loop quantum gravity, aim to describe the properties of spacetime at tiny scales and may contain clues about the nature of dark energy. Collaborative research between the theoretical physicists and cosmologists is crucial in exploring these theories and their implications for dark energy. Additionally, advancements in data analysis techniques and machine learning algorithms are enhancing our ability to extract meaningful information from vast amounts of observational data. These tools enable scientists to analyze complex datasets and identify subtle patterns, ultimately leading to a deeper understanding of dark energy. Collaborative efforts between astronomers, statisticians, and computer scientists are crucial in developing sophisticated data analysis methods and algorithms tailored to dark energy research. By fostering interdisciplinary collaborations and embracing emerging technologies, scientists are poised to push the boundaries of knowledge regarding dark energy. Future developments and collaborative efforts continued. Efforts to understand dark energy extend beyond observational astronomy and theoretical physics. Collaborations with experts in related fields, such as particle physics and quantum mechanics, hold potential for groundbreaking insights. One avenue of exploration involves studying the fundamental properties of particles and forces that make up our universe. By investigating the behavior of particles at high energies, scientists can gain a deeper understanding of the fundamental forces at play in the universe. Quantum gravity, a theoretical framework that seeks to reconcile the principles of quantum mechanics with gravity, also offers potential avenues for understanding dark energy. Quantum gravity theory, such as string theory and loop quantum gravity, aim to describe the properties of spacetime at tiny scales and may contain clues about the nature of dark energy. Collaborative research between the heretical physicists and cosmologists is crucial in exploring these theories and their implications for dark energy.